Let me, sorry. So as a title, the topic is supermassive black hole, and we consider a scenario of the reckless scenario, okay, from SIDM. Okay, so let's start. So there's a puzzle supermassive black hole here. So we know that supermassive black hole, sorry, supermassive black hole with a mass larger than 10 to the 8 solar mass are found at the central galaxy of the most massive galaxy. Okay, and the early formation. Okay, recently we found a lot of supermassive black hole in a realization era, which is in the redshift between 6 and 20. Okay, and this has puzzled astrophysics for decades. Okay, uh, and even more recently, around 100 of distant supermassive black holes are found around redshift 7, which is just at the age of the 800 million years after the Big Bang. Okay, okay. So here is an illustration by artists about a quasar. And the quasar is the most energetic object in astrophysics, and it's believed that it's powered by a supermassive black hole residing at the center. Okay. So conventionally, there are many mechanisms to explain supermassive black hole and its origin. Okay. Here on the right-hand side, this is a flow chart by Martin Rees in early 80s. Okay. About the different mechanism can form a supermassive black hole. I will not go through the detail, but roughly all these mechanisms can be categorized by two scenarios. One is a merger scenario. So for merger scenario, most of these supermassive black hole are formed by the seed of stellar mass black hole. Okay, so actually it requires more time to form this in this mechanism because you have to have a star first, and the remnant of that star can form a stellar mass black hole, and then they merge to become supermassive. But in this scenario, adding the accretion is required to reach a supermassive to 10 to the 8. And usually it takes too long to form a supermassive to a 10 to the 8 solar mass. Okay. So even though we can explain the supermassive black hole to reach at this high mass uh, by now, but it's hard to explain the high redshift supermassive black hole around redshift 7. Okay. And another scenario is the record scenario from pristine gas. Okay, this is a more efficient way to form a supermassive black hole. Okay, but but the problem of this scenario is that you need to have some mechanism to keep the temperature high, such that the fragmentation will not occur. And okay, so if the fragmentation occur, it will form a star. Okay, then it cannot lead to a direct collapse to a supermassive black hole. And another challenge of this scenario is that the disposal of angular momentum. Okay, and we know that because there's an upper limit of the angular momentum of a black hole. So if you cannot shed out most of the angular momentum, even though you reach the instability condition to form a black hole, it cannot really collapse directly into a black hole. Okay, let me go through this. Okay. So now we consider a scenario because there's one unknown is a supermassive black hole, and there's another unknown we don't know is a dark matter. What's the nature of dark matter? So actually, this project is like combining two unknowns into a solution. Okay, so this scenario has been discussed in the last 20 years. So we just assume that if the dark matter has self-interaction, okay, and actually, if the dark matter can have a self-interaction, it can explain some astrophysics puzzle like a Kohl's problem or diversity of the rotational curve, okay, of in astrophysics. Okay. These are some references you can refer to. Yeah, I will not go through this detail. Okay. Due to the time limit. Okay. And in order to explain the dwarf galaxy, the core profile of galaxy, which is a core cost problem, self-interaction strength is assumed to be order 1 centimeter meters square per gram. Okay. And in this project, we just consider elastic collision with okay. And you can also consider more complex scenario that the collision with dissipation. Okay. And this is the paper you can refer to, but I will focus on elastic collision. Okay. There's no dissipation. Okay. So actually, just right after this model has been proposed, there are some people discuss whether we can have a direct collapse of SIDM and to form supermassive black hole. And because the gravitationally, the dark matter halo is the gravitational bound system. So in the core region, the heat capacity is negative. So in some sense, because it is a thermalized system and is in the gravitational system, okay, and the heat flow will flow out if the density in the central region is high, and the temperature will increase because of negative heat capacity. So eventually, the core region will get the temperature will get higher, and and the density will also get higher as a heat transfer out in this system due to the collision of a SIDM. Okay, so finally, it will lead to a gravithermal contraction. So at the end of the day, it will lead to a core collapse. Okay, this scenario has been discussed by early paper by Shapiro, but the point is that in order to explain the high-risk supermassive black hole is still too long to explain the time required to lead to a direct collapse. Okay, given the cross-section order 1. Okay, cross-section strength of order 1. Okay, so there are some feature about gravithermal evolution of SIDM dark halo. So there are two proper length scale for heat transfer. Okay, because the dark matter has a if the dark matter has collision, um, we can consider two typical length scale to compare. Okay, one is the mean free path, the other one is a gravitational length scale, which is a gene scale, gene's mass, gene's length in astrophysics. So gene's length in astrophysics roughly is like if you have particle orbiting around this gravitational system, that's roughly the scale you orbit this halo, the length scale you orbit. Okay, another length scale is the mean free path. Okay, it's a collision between, it's a typical length scale between a collision of two particles. Okay. Okay, so we can compare these two length scale and characterize the heat capacity, heat conductivity, and also the viscosity. Okay, depending on which scale dominate. There are some detail. Maybe I cannot explain too much, but the point is that usually the dark halo start out from long mean free path regime because of the distance between particles is huge. Okay, so mean free path is much larger than the gene's length. Okay, but gravithermally, during gravithermal evolution, it will finally evolve into a short mean free path regime. So in this regime, it becomes more like a fluid. Okay, and finally, we will check whether this short mean free path regime will collapse into a black hole. Okay. So here are the gravithermal evolution equation of motion we use in the simulation. Okay, so basically the first equation is just a conservation of mass and also the balance between gravity and pressure. Can you see my cursor? There's no cursor there. Okay. And also some The third equation is the entropy equation. It describes how entropy uh, change according to as a function of radius. And the last equation is the heat conduction equation. Okay. So in the simulation, we use the NFW profile as the initial condition, and we evolve this system to see how the profile change during a gravitational evolution. So in the NFW profile, we have two free parameters we can tune depending on the property of a halo. So one is a scale radius, and the other one is a density. So every other physical quantity like a mass or velocity dispersion or time, okay, luminosity can be written in terms of these two parameters. Okay. Okay. So another thing I need to emphasize that um, yeah, in this project we consider scenario with a baryon. So I will explain that actually when we add a baryon, the baryon potential, gravitational potential will deepen uh, the whole gravitational potential, and it will increase the gravitational collapse. Okay, finally. So to model the baryon profile, we use a single power law by Weiss in 2008. Okay, so there are one more parameter characterize the abundance of baryon in a halo. Okay, so here's are the typical scale we choose to fit the data from simulation by Weiss. Okay, yeah. So okay, so here's a result. So as we can see from the graph on the left-hand side. So initially, the profile is NFW, the blue line. So, but eventually, as time goes by, it will evolve into a high density region at the center. Okay. So in the insert panel here, it shows that the time required for the collapse to happen. Okay. The blue line is the case with baryon. Okay. The dashed line is the case with SIDM only. Okay. So we can see the time difference. For the case with baryon, the collapse time is roughly a 8.4 Z naught, T naught. But for just pure SIDM, it takes almost 1,000 T naught. Okay. T naught can be written in terms of the MFW parameter, as I mentioned. Any question? Sorry, I saw some question. Oh, sorry, no question. So, okay, so here is just a result. Okay, so finally, the central density diverge in infinite time, but the baryon can facilitate the process. Okay. So we use this scenario from simulation to solve the high ratio supermassive puzzle. So actually there are 10 candidates observed as a quasar, but is believed to be the supermassive black hole. So we consider pressure formalism for halo mass function. So for the left end is a halo mass, and the right end of the red curve is uh, the final C black hole you can have, the mass of a final C black hole. Okay, and the black and gray curve illustrate the Edina equation history. Okay, the upper panel is is a sub Edina equation, but the lower panel is for we consider two scenarios. One is a sub Edina equation. The other one is roughly Edina equation in a okay in the equation history. So generally, we found that actually in this scenario, we can form a supermassive black hole during just 100 million years. Okay. Okay, so here we consider the halo SIDM halo roughly formed at around redshift 10. Okay, okay. But in contrast, for pure SIDM halo, it takes almost 10 giga years, okay, to form supermassive black hole. So it's longer than the age of our universe. Okay. So another thing is the direct collapse of the inner core. Because you might wonder, we consider the simulation is just Newtonian gravity. So whether the inner core will lead to the dense central region will lead to a final C black hole, we need to treat this system as a general relativity system. Okay. So now we consider independent scenario. We model the core region as from some equation state. Okay. And this is motivated by early study of global cluster. Okay. Uh, Generally, if you have a particle in a gravitational bound system, okay, and if the documented particle have high enough energy, it will evaporate from this system. So we need some quantity to characterize this effect, which is the cutoff energy in your distribution function. Okay, and this cutoff energy is related to the gravitational potential. Okay, so here is a model we consider. Generally, this model can be derived from Fokker-Planck equation, but I wanna go through the detail. Okay, so we consider classical limit as we learn in general in undergrad statistical quantum statistics. That's a constraint for this model to be classical. So we can approximate this as a classical Maxwell-Boltzmann distribution as this. If the alpha is a degeneracy parameter is much less than -1. Okay. Yeah, there's some. So maybe let me go through this. So basically, we just calculate the equation of state of this model. So from this model, we can determine the typical length scale of the core region. Okay, can be written as following. So it depends on the mass of the SIDM particle and also the degeneracy parameter at the core boundary. Okay, alpha R. And there's another parameter determining the temperature parameter at the core boundary. So generally, we consider the core in a thermal bath with a fixed temperature. And now we can solve the TOB equation, which is a general relativity version of the Newtonian gravity. And then we determine the condition, whether the general relativity GR instability is reached or not. I will explain this in later. Okay. So in general, from this equation state, we have a four independent parameter we can tune. Okay. So there are some quantity.
Sorry, Wei-Xiang, I think you should speed up. There's no time.
Sorry.
It's only
Maybe
20 minutes
just
plus 5 minutes.
here.
Yeah, forget,
Okay.
Skip all the technical details.
Okay. So basically, we determine the instability by checking the adiabatic index. Okay. So adiabatic index is important. It determines how stiff your system is and how easier you can compress the system, let the system to collapse. Okay. So in non-relativity limit, this adiabatic index is 5/3, and in relativity limit 4/3. Okay. Yeah, as we learn. So another thing is a companies. To reach a GR instability, roughly speaking, the gravitational energy is comparable to the rest mass energy of the system. Okay. So for neutron star, the companies is roughly 0.3, but it's still stable. But as I will explain, for ideal gas, actually it becomes unstable for companies to become just 10 to the minus 2. Okay. Okay. So actually, the larger the mass, the easier to collapse. Okay. Okay. So adiabatic index in Newtonian gravity, basically we solve a pulsation equation. You have a sphere. Okay. So you try to compress a sphere. So we calculate how this sphere to respond. So there's a characteristic oscillating frequency. So if the frequency omega squared is negative, we can determine the system is unstable. Okay. Okay. And in Newtonian gravity for ideal gas is the adiabatic index, as I mentioned, is around the 4/3 and 5/3. So it's hardly to occur because the critical adiabatic index is 4/3. But in GR case, something different happened because the pressure also sourcing the gravity. So actually, you will make this system more unstable. So critical adiabatic index is larger than 4/3 in a GR context. So here is the graph showing you that we fix the temperature at the boundary. Okay. So actually critical adiabatic index will increase. But for the gas, if the gas become relativistic, it will change from 5/3 to 4/3. So eventually it will meet the requirement to become unstable and collapse into a black hole. So result is that the central velocity dispersion roughly is 0.56 to reach the dynamical instability. Okay. And it will evolve adiabatic into a black hole. So there are other scenarios to consider. Maybe I will skip this detail. So yeah. So there's a internal energy we can define for gravitational system, which is just like a binding energy. And another quantity we can define is a fractional binding energy. So here we consider the other three criteria. We loop different central density, and we see what's the maximal point or the turning point of the sequence of solution by looping different central density. Okay. So here are the results. We fix the temperature at 0.1 and 0.2, 0.3, 0.5. Okay. So there are three different criteria. But the general picture is that it will meet the maximal mass and then maximal binding energy and then maximal fractional binding energy. And finally, it will meet the adiabatic index. So in this scenario, we can confirm that the adiabatic index criterion to check this instability is a sufficient condition. Okay. So here is the illustration we consider. Okay. So there are 4 different criteria to check the GR instability. Okay. So yeah, I think I don't have time to discuss angular momentum, but here is a summary. Okay. Actually, for angular momentum, because the dark matter particle has a collision, so effectively you will have a viscosity in the fluid. Uh, if it acts as a fluid, the viscosity, original viscosity from the collision of particles. So effectively, we can transport angular momentum out. Okay. So here's a summary. The origin of a supermassive black hole and the nature of dark matter are two important problems. And as a gravitational evolution system, the SIDM dark halo uh, reach the single state takes longer than the age of our universe, but the baryon potential can reduce the collapse time by a factor of 10 to 1,000. Okay, so direct collapse of supermassive black hole around 10 to the 4 to 10 to the 9 solar mass is possible before redshift 7. Okay, yeah, and also sufficient condition for inner core to collapse is a viscosity, velocity dispersion around 0.56 speed of light. Okay, so I think I will stop here. Yeah.